The morning of August 14th, 1940, above the English Channel, Flight Lieutenant James Nicholson's Hawker Hurricane took 3 cannon shells from a Messerschmitt 110. The first tore through his cockpit canopy, the second shredded his left aileron, the third punched into the gravity fuel tank mounted directly in front of his instrument panel, exactly 18 inches from his face. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What happened next would be described in his combat report as a white flash, followed by liquid fire. The fuel tank ruptured, aviation gasoline, vaporizing instantly in the summer heat, mixed with oxygen in the perfect ratio for combustion. Then came the spark. Whether from shrapnel striking metal or an electrical short didn't matter. The cockpit became a furnace. Nicholson survived. He stayed in the burning hurricane long, enough to shoot down the Messerschmitt that had hit him, then bailed out through flames at 8,000 feet. He spent 4 months in the hospital with third-degree burns covering 40% of his body. He would receive the Victoria Cross, the only fighter command pilot to earn Britain's highest award during the Battle of Britain. But he was one of the lucky ones. Between July and October 1940, the Royal Air Force lost 544 pilots killed in action. German intelligence analysis of British fighter losses suggested that 70% died not from catastrophic airframe damage, but from fuel fires. Bullets punctured tanks, tanks leaked gasoline, gasoline met ignition sources, pilots burned alive. The problem facing every Air Force in 1940 was brutally simple. You needed fuel to fly, but fuel wanted to kill you. A single rifle-caliber bullet through an unprotected fuel tank would drain 20 gallons in under 2 minutes. If tracer rounds followed, and they always did, the leaking gasoline vapor cloud ignited with enough force to blow wings off airframes. The British had tried to solve the fuel fire problem before the war started. Engineers at Fireproof Tanks Limited in Portsmouth had developed rubber-lined bladders that could seal bullet holes through a chemical reaction. When gasoline seeped into the untreated rubber layer, it caused the material to swell and plug the puncture. Self-sealing fuel tanks worked against ball ammunition standard lead-core bullets that punched clean holes. But by mid-1940, hardly anyone was using ball ammunition anymore. Both the Luftwaffe and the RAF had switched to incendiary rounds specifically designed to ignite fuel tanks on impact. Self-sealing wouldn't help if the bullet set the tank on fire before the rubber could swell shut. The Germans had figured this out first. Their 7.92mm B-Patron incendiary round, introduced in 1937, used a phosphorus-based composition that ignited from the friction heat of impact. When test-fired against British Hurricane mock-ups at Rechlin Proving Ground in early 1939, the B-Patron achieved ignition in roughly 1 shot out of every 10 against self-sealing tanks. 1 in 10 doesn't sound impressive until you remember that Messerschmitt 109s carried 2 machine guns firing at 1,200 rounds per minute combined. At close range, a 2-second burst put 40 bullets into the target. 4 hits, 4 chances to start a fire. Against older hurricanes without self-sealing tanks, the success rate climbed to nearly 1 in 5. British intelligence obtained a detailed technical report on the B-Patron in December 1939, when a Heinkel 111 bomber force-landed intact in Scotland. RAF technicians at Woolwich Arsenal disassembled the ammunition and found the phosphorus composition elegant and terrifying. It worked. It worked too well. And Britain's own incendiary ammunition was worse than useless. The Royal Air Force's standard incendiary in September 1939 was the .303 Mark IV Buckingham bullet, a design that dated to World War I. The Buckingham used white phosphorus in a hollowed bullet sealed with a brass plug and 2 small weep holes. When fired, propellant gases ignited the phosphorus through the weep holes, creating a visible smoke trail to help pilots track their aim. This sounded fine until you actually tried to use it in combat. The Buckingham had 3 fatal flaws. First, the phosphorus ignited immediately on firing, not on impact, so it couldn't reliably set fuel tanks on fire. It might burn itself out before reaching the target. Second, the burning phosphorus eroded the bullet's exterior as it flew, destroying accuracy beyond 300 yards. Third, production required hand-loading phosphorus into each individual bullet, which meant manufacturing capacity topped out at around 10,000 rounds per week. The RAF needed millions of incendiary rounds per month to arm 8-gun fighters like the Spitfire and Hurricane. The Buckingham couldn't scale. It barely worked in the first place. When France fell in June 1940 and the Luftwaffe began operating from bases just across the English Channel, RAF Fighter Command faced a crisis that wasn't about radar or pilot training or aircraft production. It was about chemistry. British fighters were shooting German bombers with ammunition that couldn't reliably ignite fuel tanks, while German fighters were shooting British aircraft with ammunition that could. The numbers from early Battle of Britain engagements backed this up. RAF guns were landing, hits, gun camera footage, and German loss records confirmed that British pilots could aim, but too many damaged German bombers were making it home. Bullets went through fuel tanks. Tanks leaked, but fires weren't starting often enough to bring down aircraft that should have been kills. Air Ministry analysis in late July 1940 broke down the effectiveness of RAF .303 ammunition against Junkers 88 and Heinkel 111 bombers. Ball ammunition, which made up roughly 40% of standard fighter loadings, did almost nothing useful. It punched holes but caused no critical damage unless it hit something vital like an engine or crew member. Armor-piercing rounds worked better. They could damage engines and penetrate self-sealing tanks, but they didn't ignite fuel. The Buckingham incendiary tracer achieved fire ignition in approximately 1 shot out of every 15 against self-sealing tanks, and 1 in 8 against unprotected tanks. Those were dismal numbers. A Spitfire carried about 2,400 rounds of .303 ammunition across 8 guns. Standard loading was 4 guns, with ball, 2 with armor-piercing, and 2 with Buckingham incendiary. That meant roughly 600 incendiary rounds total, fired in bursts lasting maybe 15 seconds. If you hit with 30 incendiary rounds, a generous estimate given that most pilots fired at longer ranges where accuracy dropped, you might get 2 fires started. Maybe. Against bombers with crews trained to fight fires and self-sealing tanks designed to limit damage, 2 fires often weren't enough. Meanwhile, German fighter pilots were setting British fighters ablaze with depressing efficiency. The Luftwaffe loaded their machine guns with a belt mixture that included 1 incendiary round for every 4 armor-piercing rounds. The incendiary worked on impact. It didn't need to burn during flight. It just needed to survive penetration through the aircraft skin and then ignite the fuel vapor inside the tank. This was the core problem facing RAF ordnance officers in August 1940. They needed an incendiary bullet that ignited on impact, not on firing. It needed to maintain accuracy at combat, ranges beyond 400 yards. It needed to be simple enough to mass-produce at rates exceeding 1 million rounds per week. And ideally, it needed to work better than what the Germans had. The solution came from an unlikely place. A Belgian inventor living in Switzerland, who walked into the British War Office in January 1938 with a briefcase full of hand-loaded demonstration rounds and a formula he wouldn't share. His name was De Wilde, and the bullet he'd invented looked unremarkable, a standard copper-jacketed Spitzer profile with no visible external differences from ball ammunition. But when British test officers fired it at fuel tank mock-ups at Woolwich Arsenal, it ignited gasoline vapour roughly 1 shot in 5, twice as effective as the Buckingham, 3 times as effective as the German B-Patron. The War Office purchased the rights to the De Wilde design in December 1938 for an undisclosed sum. Then they discovered De Wilde's ammunition was essentially impossible to manufacture. He'd made each round by hand in his Swiss workshop, measuring ingredients by feel rather than by weight. A pinch of this compound, a small amount of that powder, mixed together in proportions he'd refined through trial and error, but never written down as precise formulas. British chemists spent 6 months trying to reverse engineer the De Wilde composition. They analysed the incendiary charge under microscopy and found it contained several metallic powders mixed with an oxidizer compound, probably a nitrate salt. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But the exact ratios, the particle sizes, the pressing pressure needed to pack the mixture into the bullet, those details mattered enormously, and de Wilde either couldn't or wouldn't provide specifications compatible with industrial production. By July 1939, with war clearly imminent, the War Office handed the problem to Major Aubrey Dixon at Woolwich Arsenal's Ammunition Research Division. Dixon's instructions were straightforward: develop an incendiary bullet with the same effectiveness as the de Wilde, but using a composition that could be manufactured at scale using standard ammunition production equipment. Dixon had a background in chemical engineering and explosives, and he understood the fundamental challenge. An impact-ignited incendiary needed to accomplish three things that contradicted each other. First, it needed to be stable enough to survive being fired from a gun. The acceleration forces inside a rifle barrel peaked at 50,000 times the force of gravity. Second, it needed to be sensitive enough to ignite from the impact shock when it hit the target. Third, it needed to produce enough heat, quickly enough, to ignite gasoline vapor. The German B-Patron used phosphorus compounds that satisfied requirements 2 and 3 beautifully. Phosphorus ignites easily and burns viciously hot, but phosphorus is hideously unstable. It reacts with air at room temperature. Storing. Phosphorus ammunition requires hermetic sealing, and even then, the rounds have a shelf life measured in months. The Luftwaffe accepted this limitation because they expected to use their ammunition quickly in a short war. Britain needed ammunition that could be stockpiled for years and remain reliable. Phosphorus wasn't an option. Dixon started with a literature search through pre-war German and American chemical journals. He was looking for fuel oxidizer mixtures that generated high temperatures but remained stable during storage. Thermite, a mixture of aluminum powder and iron oxide, looked promising at first. Thermite reactions produced temperatures exceeding 4,000 degrees Fahrenheit, more than enough to ignite gasoline vapor. But thermite requires an extremely high ignition temperature. You need a magnesium ribbon or similar high-energy source to start the reaction, and the impact shock from a bullet hitting an aircraft simply wasn't energetic enough. What Dixon needed was something like thermite, but with an oxidizer more reactive than iron oxide, something that would ignite from impact friction alone. He found the answer in experiments the Germans had conducted in the early 1930s with barium nitrate. Barium nitrate is a crystalline salt, stable at room temperature, non-hygroscopic, meaning it doesn't absorb moisture from air, and it's a powerful oxidizer. When mixed with finely powdered aluminum or magnesium, barium nitrate creates a composition that will ignite from mechanical shock or friction if the particles are small enough and intimately mixed. The Germans had abandoned barium nitrate mixtures in favor of phosphorus because barium nitrate compositions were harder to ignite reliably. That was actually an advantage for Dixon's purposes. A composition that required significant impact shock to ignite meant it would survive being fired without detonating inside the gun barrel. 39 used 50% aluminum powder and 50% barium nitrate, mixed together and pressed into a brass cup at 7,000 pounds per square inch. He loaded the cup into a modified .303 bullet with the steel core drilled out to accept the incendiary charge, then sealed the assembly with a thin lead disc at the nose. The test firing took place at Woolwich's indoor range against a steel plate backed by a pan of aviation gasoline. Dixon loaded 5 rounds into a Lee-Enfield rifle and fired from 50 yards. The first round shattered the bullet on impact with the steel plate but failed to ignite. The second round also failed. The third round produced a brief spark but no sustained flame. The fourth round exploded in a brilliant white flash that lasted less than half a second too fast to ignite the gasoline. The fifth round ignited on impact and produced a jet of molten sparks that set the gasoline burning within 2 seconds. 1 success out of 5 firings. Not good enough, but promising. Dixon spent October and November 1939 running hundreds of test firings with slight variations in the composition ratio, particle size, and pressing pressure. He discovered that pure aluminum powder ignited inconsistently because aluminum forms a thin oxide coating that inhibits the reaction. Magnesium powder worked better but was prohibitively expensive. The solution was magnalium, an alloy of aluminum and magnesium, typically 50% of each metal, which combined magnesium's reactivity with aluminum's low cost. He also learned that particle size mattered enormously. The aluminum magnesium powder needed to be finer than 200 mesh, meaning particles small enough that 200 of them laid side by side would span 1 inch. Coarser powder wouldn't ignite reliably, but powder finer than 300 mesh became dangerously sensitive and could detonate during the pressing operation. By January 1940, Dixon had refined his composition to 7 grains of SR365, that was the official designation, standing for Small Arms Research Composition number 365. The formula was 50% magnalium powder at 200 to 250, mesh size, and 50% barium nitrate crystals ground to similar fineness. The mixture was pressed at 10,000 pounds per square inch into a brass cup, which was then pressed into the hollowed core of a .303 bullet and sealed with a thin aluminum disc at the nose. Test firings in February 1940 showed dramatic improvement. Against self-sealing fuel tank mock-ups at 200 yards, the SR365 incendiary achieved ignition in roughly 1 hit out of every 5. Against unprotected tanks, the success rate climbed to nearly 1 in 3. This matched the performance of the original DeWild ammunition, and it could be manufactured using standard ammunition production processes. The bullet was officially designated the .303 incendiary Mark VI. For security purposes and to confuse German intelligence, it was publicly called the DeWild round, even though the design was entirely Dixon's work. The original Belgian inventor received a financial settlement that satisfied him enough to stop complaining about his name being attached to someone else's bullet. Production authorization came through in April 1940, and the first batches reached RAF squadrons in early June, just in time for Dunkirk. Pilots reported immediate improvement. The Mark VI produced a visible flash on impact, which helped them see where their fire was going and adjust their aim. More importantly, German bombers and fighters that took hits from Mark VI rounds started burning with gratifying regularity. By August 1940, standard RAF fighter loading had evolved to 4 guns loaded with armor-piercing ammunition and 4 guns loaded entirely with Mark VI. Incendiary. The ball ammunition disappeared from the loading entirely. It didn't contribute enough to justify wasting gun capacity on it. German intelligence noticed the change. Interrogations of Luftwaffe aircrew shot down over England in August and September 1940 included repeated mentions of British fighters using explosive ammunition that seemed far more effective than earlier in the summer. Captured British ammunition was analysed at German proving grounds, and reports noted the incendiary composition was similar to previous German experimental mixtures abandoned in favour of phosphorus compounds. The Germans had developed the basic chemistry years earlier, then discarded it as insufficiently reliable. Major Dixon had made it work by controlling the variables they'd ignored: particle size, mixing intimacy, and pressing pressure. The difference between failure and success in ammunition chemistry often came down to details measured in thousandths of an inch, pounds per square inch. The Mark VI proved its worth throughout the Battle of Britain, but Dixon knew the composition had limitations. The SR365 mixture worked well in .303 rifle-caliber bullets, where the incendiary charge weighed just 7 grains, about half a gram. But American aircraft used 50 caliber machine guns that fired much larger bullets. A 50 caliber round has roughly 4 times the internal volume of a .303. That meant the incendiary charge would need to be scaled up proportionally to maintain effectiveness. More incendiary mixture meant more potential for manufacturing problems. Larger charges were harder to press uniformly. Non-uniform density meant inconsistent ignition, and magnalium powder in bulk quantities presented serious explosion hazards during production. These were problems for American chemists to solve. In December 1940, as part of an early technology sharing agreement that preceded Lend-Lease, Britain provided the United States with complete technical documentation on the SR365 incendiary composition and the Mark VI bullet design. The documentation included manufacturing specifications, test data, and Dixon's notes on the chemistry behind the composition. American ordnance officers at Frankfurt Arsenal in Philadelphia received the British documents in January 1941 and immediately recognized the implications. The United States Army Air Corps was in the process of standardizing on the .50 caliber Browning machine gun as its primary aircraft armament. Every fighter, every bomber, would carry multiple .50 caliber guns loaded with thousands of rounds. The Army had its own incendiary ammunition, the .50M1 incendiary round, which used a completely different chemical approach involving white phosphorus, similar to the old British Buckingham design. It had the same problems: inconsistent ignition, limited shelf life, and production bottlenecks. The British SR-365 composition looked like the answer. It was stable, it was effective, and it could theoretically be scaled up to .50 caliber size. But, theoretically, was doing a lot of work in that sentence. American chemists would spend the next 2 years discovering exactly how difficult it was to make Dixon's chemistry work at .50 caliber scale. They would encounter manufacturing problems that nearly shut down production multiple times. They would redesign the bullet 3 separate times, and they would eventually develop a version so effective that it would remain in frontline service for the next 80 years. But in early 1941, none of that was obvious yet. What was obvious was that the German Luftwaffe and the British RAF had both figured out how to set aircraft on fire with chemical compositions that ignited on impact, and the United States was still using ammunition based on World War I technology. American pilots, training for war in obsolete P-40 Warhawks and P-39 Airacobras, had no idea their guns would be loaded with bullets that couldn't reliably do the one thing that mattered most in aerial combat: set the enemy on fire before he set you on fire. That was about to change, thanks to a chemical composition measured in grams, mixed at ratios that had to be perfect, and pressed at pressures that would explode if anyone got careless. The chemistry of setting things on fire from 1,000 yards away turned out to be remarkably precise, and precision at scale required solving problems that Major Dixon had never encountered in his laboratory. Captain Louis Edward Johnson of Frankfurt Arsenal had a chemistry degree from MIT and 7 years of experience developing small arms ammunition when the British technical documents arrived on his desk in February 1941. He spent 3 days reading through Major Dixon's notes on the SR-365 incendiary composition, then walked down to the test range and fired 50 rounds of British .303 Mark VI ammunition at steel plates. The incendiary worked exactly as advertised: bright white flashes, consistent ignition, visible impact indicators. Everything American ordnance officers had been asking for. Johnson's assignment was simple on paper: scale the SR-365 formula up from 7 grains to roughly 35 grains to fit inside a .50 caliber armor-piercing bullet. Take Dixon's chemistry and make it American-sized. The first problem appeared immediately: magnalium powder, the 50-50 aluminum-magnesium alloy that made Dixon's composition work, wasn't something you could just order from a chemical supply catalogue. It had to be manufactured to precise specifications, with particle sizes controlled to within 20 microns. Coarser powder wouldn't ignite reliably. Finer powder became dangerously sensitive to static discharge and friction. American metallurgical suppliers, in early 1941, had exactly 0 experience producing magnalium powder at the fineness Dixon's formula required. The aluminum industry knew how to make structural alloys for aircraft frames. The magnesium industry knew how to cast engine blocks and incendiary bombs, but creating an intimate blend of both metals, ground to 250 mesh, in quantities measured in tons per month, that was new territory. Johnson contacted National Lead Company in Perth Amboy, New Jersey, which had experience producing finely divided metal powders for paint pigments. National Lead's chief chemist, a man named Harold Steinberg, agreed to take on the challenge in March 1941. He would spend the next 9 months trying to prevent his powder mills from exploding. The fundamental problem was that magnalium, when ground fine enough to pass through a 250 mesh screen, behaves less like a stable metal powder and more like a barely restrained explosive. The grinding process creates fresh metal surfaces with enormous surface area. Those surfaces oxidize instantly when exposed to air, releasing heat. In bulk quantities, that heat can accumulate faster than it dissipates. Steinberg's first attempt in April 1941 used conventional ball mills, rotating drums filled with steel balls that pulverize material through mechanical impact. He loaded 50 pounds of coarse magnalium chips into a mill, sealed it with an inert nitrogen atmosphere to prevent oxidation, and started the rotation. 6 hours into the grinding process, the mill's internal temperature climbed past 200 degrees Fahrenheit. At 200 to 30 degrees, the magnalium auto-ignited. The nitrogen atmosphere prevented a full explosion, but the mill's interior reached temperatures high enough to weld some of the steel balls into a fused mass. Steinberg tried water-cooled mills. The magnalium reacted with water vapor and ignited. He tried oil-cooled mills with the grinding chamber, submerged in mineral oil. The oil contaminated the powder and ruined its ignition characteristics. He tried cryogenic grinding with the mill chamber cooled by liquid nitrogen. That worked better. The extreme cold suppressed the auto-ignition temperature, but the process was prohibitively expensive and couldn't scale to industrial production volumes. The solution, when Steinberg finally found it in September 1941, involved accepting that the powder would generate heat and designing a process that dissipated that heat continuously. He used a modified impact mill with multiple cooling stages, grinding the magnalium in small batches of 5 pounds at a time, with forced air cooling between each grinding pass. The powder would heat up during grinding, then cool down during handling, preventing thermal accumulation. Production capacity topped out at about 200 pounds per day, barely enough to manufacture 10,000 50 caliber rounds. And each batch required constant attention from trained operators who understood that one moment of inattention could result in a powder fire that would consume the entire batch in seconds. Meanwhile, Captain Johnson at Frankfurt Arsenal was encountering his own problems, trying to load the magnalium-barium nitrate mixture into 50 caliber bullets. The British Mark VI used a 7-grain charge pressed into a brass cup that weighed less than the incendiary mixture itself. The cup could be pressed at 10,000 pounds per square inch without risk of bursting. A 50 caliber armor-piercing incendiary needed a 35-grain charge 5 times larger. Johnson's initial design used a scaled-up brass cup, but when the pressing equipment applied 10,000 psi to 35 grains of incendiary mixture, the cup walls deformed and sometimes split. Reducing the pressure to 6,000 psi kept the cup intact, but produced charges with inconsistent density. Some rounds ignited reliably, others failed, because the composition hadn't been compressed enough to ensure intimate contact between the fuel and oxidizer particles. Johnson redesigned the cup with thicker walls and reinforcing ridges. That solved the splitting problem, but created a new issue. The heavier cup altered the bullet's center of gravity and affected accuracy. Test firings at Aberdeen Proving Ground in November 1941 showed the modified bullets printing groups twice as large as standard armor-piercing rounds at 400 yards. He tried moving the incendiary charge forward in the bullet to compensate for the added weight at the rear. That restored accuracy but reduced armor penetration because the hardened steel core had to be shortened to make room for the repositioned incendiary cup. He tried using aluminum cups instead of brass to save weight. Aluminum was too soft, and the pressing operation deformed the cups unpredictably. By December 1941, Johnson had burned through 6 months and produced exactly 0 rounds that met all the requirements simultaneously. The M1 incendiary, the old white phosphorus design, was still the only 50 caliber incendiary in American service, and it was worse than useless. Production capacity remained limited, shelf life was measured in months, and pilots hated it because it produced visible smoke trails that gave away their position. Then Pearl Harbor happened, and Johnson's timeline went from eventually get this working to get this working now, or explain to Congress why American pilots are dying with inferior ammunition. The War Production Board authorized emergency funding in January 1942. Frankfurt Arsenal expanded its test facilities. National Lead Company built a second powder production line, and Johnson finally caught a break when a metallurgist at American Brass Company suggested using a copper alloy cup instead of pure brass. The copper alloy, 95% copper, 5% tin, had properties halfway between pure brass and pure copper. It was harder than brass, so it resisted deformation during pressing, but softer than the previous design, so it didn't interfere with the armor-piercing core's penetration characteristics. And crucially, it could be drawn into thin-walled cups that added minimal weight to the bullet. Test firings in March 1942 showed promising results. The new design, which Johnson designated the M8 armor-piercing incendiary, achieved penetration equivalent to the standard M2 armor-piercing round against homogeneous steel plate up to 3/4 of an inch thick, and the incendiary reliably ignited on impact, producing a visible flash and enough heat to ignite gasoline vapor within 2 seconds of penetration. Production authorization came through in May 1942, and Frankfurt Arsenal started manufacturing M8 rounds at a rate of about 50,000 per month, which sounds impressive until you realize the Army Air Force was requesting 5 million rounds per month to supply the bomber fleets being assembled for operations over Europe. The gap between demand and capacity was catastrophic. 5 million rounds per month required magnalium powder production to increase by a factor of 100. It required bullet manufacturing capacity to expand from a single production line at Frankfurt to multiple plants across the country. And it required solving quality control problems that hadn't even been identified yet, because no one had ever tried to manufacture incendiary ammunition at this scale. The War Department turned to Lake City Ordnance Plant in Independence, Missouri, a massive ammunition factory operated by Remington Arms that had opened in April 1941, specifically to handle large-scale production. Lake City had the floor space, the machinery, and the workforce to scale up M8 production, but they lacked experience with incendiary compositions. Frankfurt Arsenal sent technical teams to Lake City in June 1942 to train plant operators on handling magnalium powder. The safety briefings emphasized 3 points repeatedly. Never allow static discharge near the powder, never allow the powder to accumulate heat, and never, under any circumstances, allow ferrous metal tools to contact the powder during processing. A single spark could ignite the entire batch. The first production run at Lake City in July 1942 resulted in 3 fires and 0 acceptable ammunition. The fires weren't explosions. The quantities involved were small enough that combustion stayed localized, but they destroyed thousands of dollars of equipment and made it clear that scaling up incendiary production would require more than just copying Frankfurt's procedures. The problem was workforce experience. Frankfurt Arsenal employed ammunition specialists who'd spent years learning the nuances of handling sensitive materials. Lake City employed whoever the Selective Service hadn't drafted, primarily women with no industrial experience beyond assembly line work, and men over draft age who'd previously worked in agriculture or light manufacturing. These weren't stupid people. They were perfectly capable of following procedures. But incendiary ammunition manufacturing required developing an intuitive feel for when something was wrong before instruments could measure it. An experienced operator could tell from the sound of a pressing ram whether the mixture was compressing evenly. They could identify powder that had begun to deteriorate from subtle changes in color or texture. They could sense when equipment was running too hot, even if temperature gauges showed normal readings. Training a workforce to develop those instincts would take months. The War Department needed production now. The solution was to simplify the process until it could be executed by rote procedure without requiring operator judgment. Frankfurt Arsenal engineers spent August and September 1942 redesigning the M8 production sequence to eliminate steps that required experience-based decisions. They developed automated pressing equipment that shut down automatically if temperature or pressure readings deviated from specified ranges. They created visual inspection protocols with color-coded samples showing acceptable and unacceptable powder conditions. They installed continuous monitoring systems that tracked every variable in the production chain and flagged anomalies before they became fires. By October 1942, Lake City had achieved steady production of approximately 200,000 M8 rounds per week, still nowhere near the 5 million monthly target, but adequate to begin supplying operational units deploying to combat zones. The first M8 ammunition reached the 8th Air Force in England in December 1942, mixed into ammunition belts at a ratio of 1 incendiary round per 4 armor-piercing rounds. Bomber gunners reported immediate improvement over the old M1 phosphorus incendiary. The M8 produced bright flashes on impact that helped gunners confirm hits, and German fighters that took multiple M8 hits started showing increased vulnerability to fuel fires. But the real test wouldn't come until American fighters encountered Luftwaffe opposition in significant numbers. That would happen in early 1943, when P-38 Lightnings and P-47 Thunderbolts began flying escort missions over occupied Europe, their 50-caliber guns loaded with ammunition that could finally match what the British had been using for 2 years. The problem with testing ammunition effectiveness in combat is that it's almost impossible to isolate variables. When a German Messerschmitt 109 takes fire from a P-47's 850 caliber guns and goes down in flames, was it the M8 incendiary that ignited the fuel tanks? Or would armor-piercing rounds have achieved the same result by punching through the fuel system and creating spark-generating metal fragments? The Army Air Force commissioned a study in March 1943 to analyze gun camera footage and pilot reports from European theater combat. The goal was to determine whether the M8 incendiary was actually improving kill rates, or if pilots were just more confident because they could see their hits lighting up the target. The study analyzed 214 confirmed fighter kills between January and March 1943. In 68 cases, roughly 30% gun camera footage showed visible fire erupting from the target aircraft within 5 seconds of hits being scored. In 41 of those 68 cases, the fire appeared to originate from the wing or fuselage fuel tank areas rather than the engine. This suggested the M8 was reliably igniting fuel when it penetrated tank structures. More telling was the comparison between ammunition belt compositions. Fighter groups that loaded higher percentages of M8 incendiary up to 1 incendiary per 3 armor-piercing rounds showed slightly higher kill rates per engagement than groups using the standard 1-to-4 ratio. The difference was small, maybe 5 to 7%, but statistically significant across hundreds of engagements. German aircraft designers noticed. Luftwaffe technical reports from mid-1943 referenced American use of impact-igniting incendiary ammunition similar to British designs, and recommended increased emphasis on self-sealing fuel, tank protection. Some German fighters began incorporating additional fire suppression systems, nitrogen purging of empty tank spaces, automatic fuel shut-off valves that activated when bullet impacts were detected. These countermeasures worked well enough that by late 1943, the effectiveness of M8 incendiary against properly protected German aircraft had declined somewhat. But the Japanese in the Pacific theater had taken a completely different approach to fighter design that would make the M8 devastatingly effective. Japanese naval aviation doctrine in the late 1930s prioritized range and maneuverability above all else. The Mitsubishi A6M0 fighter could fly over 1,700 miles on internal fuel and outturn any Allied fighter in a dogfight. It achieved this performance through ruthless weight reduction, no armor plating for the pilot, no self-sealing fuel tanks, airframe structures built from lightweight alloys that prioritized minimum weight over impact resistance. The Zero was an extraordinary aircraft when attacking. It was a death trap when defending. American pilots in the Pacific learned this early in 1942 during engagements over New Guinea and the Solomon Islands. Zeros could absorb hits from 50 caliber ball and armor-piercing ammunition and keep flying. But a single M8 incendiary hit to a fuel tank or fuel line almost always resulted in catastrophic fire. The reason came down to engineering priorities. German self-sealing fuel tanks used multiple layers of rubber compounds that would swell when exposed to gasoline, plugging bullet holes before significant leakage occurred. The system added weight, roughly 15 to 20% of the fuel tank's empty weight, but prevented fires in most cases when tanks were hit by non-incendiary ammunition. Japanese designers had calculated that the range penalty from adding self-sealing tanks would reduce the Zero's combat radius below acceptable levels. They chose to accept the fire vulnerability and train pilots to avoid getting hit in the first place through superior maneuverability. This worked fine against poorly trained Allied pilots in early war engagements. It worked terribly against experienced American pilots using tactics specifically designed to exploit the Zero's weaknesses. By mid-1943, Pacific Theater fighter groups had developed the boom and zoom tactic diving attacks from altitude that used the American fighters' superior speed and firepower to score hits before the Zero could engage its maneuverability advantage. P-38. Lightnings particularly excelled at this approach. 4 50-caliber guns and one 20mm cannon concentrated in the nose, all loaded with ammunition designed to penetrate and ignite. Combat reports from Marine Fighting Squadron 214, the famous Black Sheep Squadron commanded by Major Gregory Boyington, provide detailed accounts of M8 effectiveness against Zeros. In a single engagement on October 17, 1943, over Kahili Airfield, Black Sheep pilots claimed 21 Zero fighters destroyed for the loss of 3 F-4U Corsairs. Gun camera analysis confirmed 18 of those kills, and in 16 cases, Japanese fighters showed visible fire within seconds of taking hits. One pilot's report specifically noted, "I fired a 2-second burst into the Zero's fuselage from about 400 yards astern, saw strikes and flashes on the target. The Zero immediately began trailing white smoke from the wing root area, which turned to orange flame within maybe 3 seconds. The entire aircraft was burning by the time it entered a spin. No parachute observed. The white smoke followed by orange flame was the signature of fuel igniting from M8 hits. The incendiary composition produced enough heat to vaporize gasoline into a flammable mist, which then ignited and spread rapidly through the fuel tank's empty space. Without self-sealing protection or fire suppression systems, Japanese aircraft typically had less than 30 seconds from initial ignition to structural failure as fire consumed wooden components and melted aluminum airframes. American pilots called it flaming a Zero. And by late 1943, it had become so routine that, after-action reports often noted simply, 2 Zeeks flamed, or flamed 1 Hamp at low altitude, without providing detailed descriptions. The M8 incendiary had become the standard tool for defeating Japanese fighters, and combat tactics evolved around maximizing its effectiveness. The Pacific Theater's success created a strange dynamic. In Europe, the M8 was a useful but not decisive advantage against properly armored German aircraft. In the Pacific, it was arguably the single most important factor in American air superiority after mid-1943. Japanese fighters could outturn American aircraft. They could outclimb them at low speeds, but they couldn't survive getting hit by ammunition specifically designed to set them on fire. Manufacturing problems persisted through 1944, despite increased production capacity. The magnalium powder remained the bottleneck. National lead companies' production lines could produce enough powder for about 1.5 million M8 rounds per month, well short of the 3 to 4 million monthly demand from combat theaters. And quality control issues meant that roughly 5 to 8% of manufactured rounds failed ignition tests and had to be scrapped. The powder failures traced back to contamination problems. Magnalium oxidizes rapidly when exposed to air, forming a thin oxide coating on each particle. That coating inhibits ignition. Fresh powder worked beautifully. Powder that had been in storage for more than 3 months started showing degraded performance. Powder stored in humid conditions deteriorated even faster. Frankfurt Arsenal chemists tried various protective coatings, mineral oil treatments, paraffin wax shells, specialized lacquers. None worked well enough to extend storage life beyond 6 months. The solution ended up being logistical rather than chemical. Ammunition plants produced M8 rounds continuously and shipped them to combat theaters within weeks of manufacture. Units in the field were instructed to use older ammunition first and report any rounds that failed to ignite, so production batches could be tracked. This created an unusual situation where M8 ammunition had an informal expiration date. Armament officers learned to check manufacturing dates and prioritize older lots for training use, while reserving recently manufactured ammunition for combat operations. It worked, but it added complexity to supply chains that were already struggling to keep pace with combat consumption rates. The ultimate validation of the M8 design came not from American analysis, but from Soviet and German responses. In 1944, the Soviet Union received samples of M8 ammunition through Lend-Lease and immediately began reverse engineering the composition. Soviet chemists at Scientific Research Institute No. 6 in Moscow analyzed the magnalium barium nitrate mixture and developed their own version, which they designated B-32 armor-piercing incendiary for use in 12.7mm heavy machine guns. The Soviet copy wasn't exact, they used slightly different particle sizes and pressing pressures, but the fundamental chemistry was identical to Dixon's SR-365 composition. By early 1945, Soviet factories were producing B-32 ammunition at rates exceeding American M8 production, and the round remained in Soviet service through the Cold War. German ordnance officers also analyzed captured M8 ammunition and filed detailed technical reports that survive in post-war archives. A Luftwaffe document from October 1944 describes the American incendiary as significantly more effective than previous phosphorus designs, and notes that the composition ignites reliably on impact, without requiring initiator charges. The report recommended immediate development of German equivalents, but by late 1944, Germany's chemical.com industry lacked the capacity to manufacture specialty powders at scale. The M8 remained in American service long after World War II ended. During the Korean War, F-51 Mustangs, the redesignated P-51, flew ground attack missions with guns loaded primarily with M8 ammunition. The incendiary proved effective against North Korean fuel dumps, vehicle concentrations, and supply depots. The ability to start fires at range with machine gun fire was valuable for interdiction missions, where pilots needed to destroy targets quickly without making multiple passes. Production continued through the 1950s, with manufacturing gradually shifting from wartime ordnance plants to Lake City, which became the sole American source for .50 caliber ammunition. The M8 underwent minor modifications, improved sealing to extend storage life, slightly refined composition ratios to improve ignition consistency, but the core design remained Major Dixon's SR-365 chemistry scaled up to American specifications. By the 1960s, the M8 was being replaced by the M20 armor-piercing incendiary tracer, which combined the incendiary function with a tracer element for observation purposes. But many M8 rounds remained in inventory through the Vietnam War and beyond. The last documented combat use was during the First Gulf War in 1991, when AC-130 gunships expended stockpiled M8 ammunition during night interdiction missions. Modern .50 caliber incendiary ammunition still uses variations of the magnalium barium nitrate composition that Captain Johnson finalized at Frankfurt Arsenal in March 1942. The pressing techniques have improved. The quality control is better. But the fundamental chemistry 50% fuel, 50% oxidizer, intimate mixing, controlled particle size, remains unchanged because it represents an elegant solution to a difficult problem. Setting enemy aircraft on fire from 400 yards away requires chemistry that's stable enough to survive being fired from a gun, sensitive enough to ignite from impact shock, and energetic enough to vaporize gasoline. Magnalium and barium nitrate, mixed at precise ratios and pressed at precise pressures, does exactly that. It's chemistry that saves lives by ending fights quickly and decisively. The British figured it out first during the Battle of Britain, when RAF pilots needed better ammunition to fight off the Luftwaffe. Major Aubrey Dixon made it work at scale by understanding that consistency mattered more than exotic ingredients. Captain Lewis Johnson made it American by solving manufacturing problems that threatened to prevent mass production. And millions of rounds later, pilots flying combat missions over Europe and the Pacific had ammunition that gave them a fighting chance against enemies who'd previously held the advantage. The story of the M8 isn't about wonder weapons or secret formulas. It's about grinding metal powder fine enough that it becomes explosive. It's about pressing powder charges to exact pressures so they'll ignite consistently. It's about training factory workers to handle materials that could burn them alive if they made mistakes. It's about accepting that some solutions can't be rushed and some problems can't be solved by throwing money at them. But mostly, it's about chemistry measured in grams, mixed carefully, and delivered at 2,800 feet per second into targets that thought they were safe because earlier ammunition hadn't worked well enough. The M8 armor-piercing incendiary changed that calculation permanently, and the math was simple. Impact plus friction equals heat. Heat plus fuel plus oxidizer equals fire. Fire equals victory. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.